All right, so now we are in chapter 3, solids, liquids, and gases. Carpenters use a level to find out if a surface is perfectly horizontal. When a carpenter places the level on a surface that is perfectly horizontal, the air bubble stays in the middle of the horizontal tube. The metal, made out of alcohol, and air in the level represent 3 states of matter. So there you go. How can shape and volume be used to classify materials? Materials can be classified as solids, liquids, and gases based on whether their shapes and volumes are definite or variable. Solids. What do these 4 objects have in common? A pencil, a quarter, a book, and a cafeteria tray. They all have a recognizable shape, and they all take up a certain amount of space. The materials in these objects are all in the solid state. Solid is the state of matter in which materials have a definite shape and a definite volume. Samples of solid copper have definite volume. Copper atoms are packed close together in an orderly arrangement. Almost all solids have some type of orderly arrangement of particles at the atomic level. Liquids. How good are you at estimating whether the juice remaining in an almost empty bottle will fit in a glass? The shape of the liquid changes as you move it from one container to the other. A liquid always has the same shape as its container and can be poured from one container to another. Liquid is the state of matter in which a material has a definite volume, but not a definite shape. So the volume never changes, but it takes the shape of its container. At room temperature, mercury is a liquid. Drops of mercury on a flat, clean surface have a round shape. Mercury in a container has the same shape as its container. The mercury atoms are close together, but their arrangement is more random than the arrangement of atoms in solid copper. As you can see, this is going to be the arrangement. They're going to be kind of like flowing, if you will. Gases. If you were asked to name a gas, what would you say? Air, which is a mixture of gases, is probably the most obvious example. Gas is the state of matter in which a material has neither a definite shape nor a definite volume. A gas takes the shape and volume of the container it is in. These balloons are filled with helium, a colorless gas that is less dense than air. 2 of the balloons are teardrop shaped and 2 are disc shaped. The shape of the helium in the balloon is the same as the shape of the balloon itself. The volume of the helium in the balloon is equal to the volume of the balloon. These balloons are filled with helium, a colorless gas. Oh, sorry, just read that. Here's the gas inside. You can see they take the shape of the container they are in this case, the balloon. The helium atoms in a balloon are not arranged in a regular pattern. They are at random locations throughout the balloon. Because of the space among helium atoms, a large amount of helium can be compressed into a metal cylinder. When helium flows from the cylinder into the balloon, the helium atoms spread out. The helium can fill balloons with much more volume than the cylinder. Other states of matter. About 99% of all matter in the universe exists in a solid state that is not as common on Earth as solids, liquids, and gases. At extremely high temperatures, such as those found in stars, matter exists as plasma. At temperatures near negative 273 degrees Celsius, groups of atoms behave as though they are a single particle. This 5th state of matter is called a Bose-Einstein condensate, or a BEC. Why was mercury used in thermometers? Until recently, mercury thermometers were used in homes and schools. Because mercury is a toxic substance that can harm humans and other organisms, schools no longer use mercury thermometers, and people are encouraged to replace their fever thermometers. How can kinetic theory? How can kinetic theory and forces of attraction be used to explain the behavior of gases, liquids, and solids? Kinetic energy is the energy an object has due to its motion. So the kinetic theory of matter says that all particles of matter are in constant motion. A ball thrown at 137 kilometers per hour has more kinetic energy than a ball thrown at 125 kilometers per hour. According to the kinetic theory of matter, particles inside the solid baseball are also moving. The kinetic theory was developed to explain the behavior of gases. It can also help to explain the behavior of liquids and solids. How can kinetic theory and forces of attraction be used to explain the behavior of gases, liquids, and solids? The motion of billiard balls can be compared to the motion of particles in a gas. The cue strikes a ball, and the ball moves in a straight line until it strikes the side of the table or another ball. When a moving ball strikes a ball at rest, the first ball slows down, and the second ball begins to move. kinetic energy is transferred during those collisions. This photograph was taken just after the cue struck the white ball, which began to move toward the white. The white ball moved in a straight line until it collided with a dark blue ball. So you can see these collisions occurring. Unlike billiard balls, the particles in a gas are never at rest. At room temperature, the average speed of the particles in the sample of gas is about 1,600 kilometers per hour. The use of the term average is a clue that not all particles are moving at the same speed. Some particles are moving faster than the average speed, and some are moving slower than the average speed. This illustration shows the possible paths of two helium atoms in a container of helium gas. Each atom moves in a straight line until it collides with the other atom or the container. During a collision, one atom may lose kinetic energy while the other atom gains kinetic energy, but the total kinetic energy of the atoms remains the same. So if this one loses, that one gains, and so forth, as the particle hits the sides of the container. If it loses kinetic energy, the particle picks up that energy. If the energy gets too great, obviously the glass would break. There are forces of attraction among the particles in all matter. Between collisions, why doesn't one particle in a gas affect the other particles in the gas? If the particles are far apart and moving fast, as in a gas, the attractions are too weak to have an effect. Under ordinary conditions, scientists can ignore the forces of attraction in a gas, and in fact we do. The constant motion of particles in a gas allow a gas to fill a container of any shape or size. The kinetic theory explains the general properties of a gas. So, particles in a gas are in constant motion. The motion of one particle is unaffected by the motion of other particles unless they collide. Forces of attraction among particles in a gas can be ignored under ordinary conditions. So those are general properties that the kinetic theory explains. How can kinetic theory and forces of attraction be used to explain the behavior of gases, liquids, and solids? The particles in liquids also have kinetic energy. So why does a liquid such as mercury have a definite volume at room temperature instead of expanding to fill its container? The average speed of a mercury atom is much slower than the average speed of a helium atom at the same temperature. The particles in a liquid are more closely packed than the particles in a gas. Therefore, attractions between the particles in the liquid do affect the movement of the particles. Therefore, attractions between the particles in the liquid do affect the movement of the particles. Kind of a repeat there, but understand that because they move slower, they can become attracted to each other. That's what makes a liquid a liquid. A mercury atom in liquid mercury can be compared to a student in a crowded hallway. The student's path may be blocked by students moving in the other direction. The student's ability to move is affected by interactions with other students. A liquid takes the shape of its container because particles in the liquid can float in new locations. The volume of a liquid is constant because forces of attraction keep the particles close together. In a liquid, there is a kind of tug-of-war between the constant motion of particles and the attractions among particles. This tug-of-war explains the general behavior of liquids. Because forces of attraction limit the motion of particles in the particles in the liquid cannot spread out and fill a container. So they're moving back and forth because of the attractions, and because of moving slow enough, the forces of attraction do count. How can kinetic theory and forces of attraction be used to explain the behavior of gases, liquids, and solids? Solids have a definite volume and shape because particles in a solid vibrate around fixed locations. Vibration is a repetitive back and forth motion. Think about the atoms in solid copper. Strong attractions among the copper atoms restrict their motion and keep each atom in a fixed location relative to its neighbors. Each atom vibrates around its location, but it does not exchange places with a neighboring atom. You might compare the particles in a solid to a polite audience in a movie theater. Although people move around in their seats, each person remains in essentially the same location during the movie. They have fixed locations in a total volume that does not change. So they stay in their seats, but they can move in their individual seats.